AI/ML model, detailed explanation of each label from the perspectives of project management, PMP, management, and AI/ML development. In the semiconductor manufacturing industry.
Pradeep K, Suri. Author, researcher, and AI or ML architect.
1. Design and development. PMP, this is the initial stage where project requirements are gathered, feasibility is assessed, and detailed designs are developed. It involves stakeholder alignment and defining the project scope. Management focus is on resource allocation, cost estimation, and ensuring that the product aligns with market needs. AI/ML developer, this stage could involve defining algorithms, data collection strategies, and preparing training datasets to ensure the model meets the product's requirements. 2. Raw material procurement. PMP ensures timely procurement of raw materials or resources necessary for the project as per the planned schedule. Management emphasizes vendor management, cost control, and ensuring quality in procurement processes. AI/ML developer, in AI terms, this could translate to acquiring relevant datasets, tools, or APIs needed for development. 3. Wafer fabrication. PMP represents a critical operational stage where raw materials are transformed into functional wafers, adhering to predefined quality metrics. Management ensures smooth operations, monitoring of yield, and minimizing wastage. AI/ML developer, in AI, this might involve initial data preprocessing or pipeline design to fabricate usable inputs for the model. 4. Etching. PMP refers to specific processing of wafers to etch circuits, which requires precision and adherence to standards. Management focus is on process efficiency and maintaining accuracy to reduce defects. AI/ML developer could refer to refining or cleaning datasets, removing irrelevant features or noise to improve model training. 5. Deposition. PMP adding layers or materials during fabrication, ensuring each layer meets specifications. Management monitors layering consistency and overall process efficiency. AI/ML developer, equivalent to feature engineering, adding new layers of data, features, to enhance the model. 6. Lithography. PMP, using light to transfer circuit patterns to wafers, a stage requiring high precision. Management ensures technological upgrades and avoids bottlenecks in high-tech processes. AI/ML developer relates to applying algorithms that provide structure or mapping for the data akin to model design. 7. Wafer inspection. PMP, post-fabrication quality control, ensuring no defects in the manufactured wafers. Management focuses on quality assurance protocols and reducing defect rates. AI/ML developer, this could involve validation of datasets or debugging code to ensure correctness. 8. Electrical testing. PMP, verifying the electrical functionality of fabricated wafers. Management ensures reliability and readiness of components before assembly. AI/ML developer, this could involve testing the model for accuracy, precision, and other performance metrics. 9. Yield analysis. PMP, analyzing the output yield from the fabrication process, identifying areas for improvement. Management focuses on maximizing returns and improving process efficiency. AI ML developer, analyzing the performance of the AI ML system and refining it for better results. 10. Packaging. PMP, encapsulation of the product for protection and usability. Management ensures the product meets regulatory standards and customer expectations. AI ML developer, deployment of AI models into production environments, wrapping them in user-friendly APIs or applications. 11. Final testing. PMP, comprehensive testing to ensure the product meets all requirements before release. Management ensures that quality checks align with organizational and market standards. AI ML developer, final evaluation of the AI model against real-world data, ensuring robustness. 12. Distribution. PMP, coordinating logistics and supply chain for delivering the product to customers. Management optimizes delivery timelines, costs, and customer satisfaction. AI ML developer could represent distributing the trained AI model or system across servers or cloud environments. 13. Customer engagement. PMP, establishing feedback mechanisms and ensuring customer satisfaction post-delivery. Management focus on building relationships and ensuring the product addresses customer needs. AI ML developer, monitoring user feedback, analyzing logs, and improving the model based on real-world data. 14. Feedback integration. PMP, utilizing customer feedback to refine the product or process. Management ensures a closed-loop system for continuous improvement. AI ML developer, incorporating feedback to retrain models, improve accuracy, or add new features. 15. Sustainability. PMP, introducing practices that make processes and products more environmentally friendly. Management ensures alignment with corporate social responsibility (CSR) goals. AI ML developer, ensuring energy-efficient model training and deployment, reducing computational costs. 16. Process monitoring. PMP, continuously tracking performance and adherence to plans. Management uses KPIs and metrics to ensure operational efficiency. AI ML developer, monitoring model performance in production, ensuring stability and scalability. 17. Defect analysis. PMP, investigating defects to identify root causes and prevent recurrence. Management aims to reduce operational losses and improve quality control processes. AI ML developer, analyzing failed predictions, debugging code, and refining algorithms. 18. Supply chain management. PMP, managing the entire chain of production and distribution. Management focuses on optimizing inventory, suppliers, and delivery timelines. AI ML developer, building predictive models to forecast supply demand or manage inventory effectively. 19. Regulatory compliance. PMP, ensuring all processes meet industry and legal standards. Management reduces risks and protects the company's reputation. AI ML developer, ensuring models comply with data privacy laws, like GDPR, and ethical AI standards. 20. Market deployment. It's the company's reputation. PMP, the final stage where the product is made available to the market. Management manages product launch strategies and market penetration. AI ML developer, deployment of models in live systems for customer interaction and decision making. This detailed breakdown shows how these labels represent stages in a project lifecycle while connecting management and AI ML practices. Each phase can be tailored to optimize workflow and enhance product outcomes. AI ML model labels for the nodes. These labels represent various stages and components in the semiconductor manufacturing process. Design and development. Raw material procurement. Wafer fabrication. Etching. Deposition. Lithography. Wafer inspection. Electrical testing. Yield analysis. Packaging. Final testing. Distribution. Customer engagement. Feedback integration. Sustainability. Process monitoring. Defect analysis. Supply chain management. Regulatory compliance. Market deployment. Here's a brief explanation of each of the labels in the semiconductor manufacturing process. Design and development. This phase involves creating the initial design and blueprint of the semiconductor product. It includes defining the product specifications, circuit designs, and selecting the appropriate materials and technologies. Raw material procurement. This step focuses on sourcing and acquiring the raw materials required for semiconductor production, such as silicon wafers, chemicals, metals, and other essential materials. Wafer fabrication. In this stage, the raw silicon wafers are processed to create the initial structure of semiconductor devices. It involves cleaning, polishing, and preparing the wafers to receive layers of material in the subsequent steps. Etching. Etching is the process of removing material from the wafer surface to create the required patterns. This is done using chemical etching or plasma etching techniques to define the components and circuits. Deposition. Deposition involves adding thin layers of material onto the wafer surface to create the necessary components. Techniques like chemical vapor deposition, CVD, or physical vapor deposition, PVD, are used for this purpose. Lithography. This process uses light to transfer the intricate designs of circuits onto the wafer. Photolithography is the most common method, where light-sensitive chemicals are applied to the wafer and a mask with the design is exposed to light. Wafer inspection. After the wafer is processed, it is inspected for defects, contamination, and quality. This stage ensures that the wafers meet the required specifications and are free from any errors. Electrical testing. Electrical testing ensures that the semiconductor devices function as expected by applying electrical signals and measuring the output. It identifies faults in the circuits and ensures the components meet operational standards. Yield analysis. Yield analysis involves determining the number of good chips or devices produced versus the total number of wafers processed. This helps identify inefficiencies or defects in the manufacturing process. Packaging. Packaging refers to the process of enclosing the semiconductor device in a protective casing that allows for electrical connections to external systems. This ensures the device is durable, functional, and safe for integration into end-use products. Final testing. In this stage, fully packaged devices undergo a series of final tests to ensure they meet performance, quality, and reliability standards. Any issues detected are addressed before shipment. Distribution involves shipping the final tested semiconductor devices to customers, suppliers, or assembly plants for use in electronic products or systems. Customer engagement. This stage focuses on building relationships with customers, understanding their needs, and providing support during product implementation. It also includes collaboration for future product development. Feedback integration. Feedback integration involves collecting customer feedback on product performance and using this information to improve future versions of the semiconductor device or the manufacturing process. Sustainability. Sustainability refers to minimizing the environmental impact of semiconductor production by reducing waste, energy consumption, and harmful emissions, while also ensuring resource efficiency and promoting recycling. Process monitoring. This involves continuous monitoring of the manufacturing process to ensure that all stages meet quality and efficiency standards. It includes tracking parameters like temperature, pressure, and material usage to optimize production. Defect analysis. Defect analysis focuses on identifying and analyzing defects in the semiconductor products. It helps determine the root cause of issues, whether they are due to design, material, or manufacturing problems. Supply chain management. Supply chain management ensures the smooth and efficient flow of raw materials, components, and finished products throughout the production process. This includes managing suppliers, logistics, inventory, and scheduling. Regulatory compliance. This involves adhering to industry regulations, standards, and legal requirements related to the production and sale of semiconductor products. Compliance ensures product safety, quality, and ethical business practices. Market deployment. Market deployment refers to the process of launching semiconductor products into the market, including sales, marketing, and customer support. This stage focuses on maximizing market reach and ensuring successful product adoption. Each of these stages plays a crucial role in semiconductor manufacturing, ensuring that the final product meets performance, quality, and sustainability standards, while also addressing customer needs and regulatory requirements. Source and target arrays. These arrays define the flow between different stages. Source, the starting point of each connection. Target, the end point of each connection. Connections. Design and development to raw material procurement, Node 0 to Node 1. Raw material procurement to wafer fabrication, Node 1 to Node 2. Wafer fabrication to etching, Node 2 to Node 3. Wafer fabrication to deposition, Node 2 to Node 4. Deposition to lithography, Node 4 to Node 5. Lithography to wafer inspection, Node 5 to Node 6. Wafer inspection to electrical testing, Node 6 to Node 7. Electrical testing to yield analysis, Node 7 to Node 8. Yield analysis to packaging, Node 8 to Node 9. Packaging to final testing, Node 9 to Node 10. Final testing to distribution, Node 10 to Node 11. Distribution to customer engagement, Node 11 to Node 12. Customer engagement to feedback integration, Node 12 to Node 13. Feedback integration to sustainability, Node 13 to Node 14. Design and development to process monitoring, Node 0 to Node 15. Process monitoring to defect analysis, Node 15 to Node 17. Raw material procurement to supply chain management, Node 1 to Node 18. Process monitoring to regulatory compliance, Node 15 to Node 19. Sustainability to market deployment, Node 14 to Node 19. Summary. This setup creates a detailed process flow from the initial design phase to market deployment, incorporating key stages like raw material procurement, fabrication steps, testing, packaging, distribution, and ongoing feedback and sustainability efforts. Each connection helps illustrate the sequential and interrelated steps involved in semiconductor manufacturing. The image is a detailed flowchart titled Semiconductor Industry Process Flow created by Pradeep K, Suri, AI/ML architect. It visually represents the various stages involved in the semiconductor manufacturing process. Here's a detailed breakdown of each stage. Stages in semiconductor manufacturing. Design and development. Purpose: creating the blueprint for the semiconductor device. Activities: circuit design, simulation, and layout design using specialized software tools. Raw materials. Purpose: procuring and preparing the raw materials needed for manufacturing. Activities: sourcing high-purity silicon and other essential materials. Wafer fabrication. Purpose: transforming raw silicon into wafers, which serve as the substrate for semiconductor devices. Activities: slicing silicon ingots into thin wafers, polishing, and cleaning them. Deposition. Purpose: adding thin layers of materials onto the wafer. Activities: techniques like chemical vapor deposition, CVD, and physical vapor deposition, PVD. Lithography. Purpose: transferring the circuit design onto the wafer. Activities: coating wafers with photoresist, exposing them to ultraviolet light through a mask, and developing the pattern. Wafer inspection. Purpose: ensuring the wafer meets quality standards. Activities: using advanced microscopy and other inspection tools to detect defects. Electrical testing. Purpose: verifying the functionality of the circuits on the wafer. Activities: performing electrical tests to check for proper operation. Yield analysis. Purpose: evaluating the production yield and identifying areas for improvement. Activities: analyzing the number of functional chips produced and identifying defects or inefficiencies. Packaging. Purpose: protecting the semiconductor chip and preparing it for integration into devices. Activities: encapsulating the chip in a protective casing and adding connections. Final testing. Purpose: performing final quality checks before distribution. Activities: testing the packaged chip to ensure it meets performance specifications. Distribution. Purpose: delivering the finished semiconductor chips to customers. The image is a detailed flowchart titled Semiconductor Industry Process Flow created by Pradeep K, Suri, AI/ML architect. It visually represents the various stages involved in the semiconductor manufacturing process. Here's a detailed breakdown of each stage. Stages in semiconductor manufacturing. Design and development. Purpose: creating the blueprint for the semiconductor device. Activities: circuit design, simulation, and layout design using specialized software tools. Raw materials. Purpose: procuring and preparing the raw materials needed for manufacturing. Activities: sourcing high-purity silicon and other essential materials. Wafer fabrication. Purpose: transforming raw silicon into wafers, which serve as the substrate for semiconductor devices. Activities: slicing silicon ingots into thin wafers, polishing, and cleaning them. Deposition. Purpose: adding thin layers of materials onto the wafer. Activities: techniques like chemical vapor deposition, CVD, and physical vapor deposition, PVD. Lithography. Purpose: transferring the circuit design onto the wafer. Activities: coating wafers with photoresist, exposing them to ultraviolet light through a mask, and developing the pattern. Wafer inspection. Purpose: ensuring the wafer meets quality standards. Activities: using advanced microscopy and other inspection tools to detect defects. Electrical testing. Purpose: verifying the functionality of the circuits on the wafer. Activities: performing electrical tests to check for proper operation. Yield analysis. Purpose: evaluating the production yield and identifying areas for improvement. Activities: analyzing the number of functional chips produced and identifying defects or inefficiencies. Packaging. Purpose: protecting the semiconductor chip and preparing it for integration into devices. Activities: encapsulating the chip in a protective casing and adding connections. Final testing. Purpose: performing final quality checks before distribution. Activities: testing the packaged chip to ensure it meets performance specifications. Distribution. Purpose: delivering the finished semiconductor chips to customers or distribution centers. Activities: packaging the chips for shipment and managing logistics. Customer. Purpose: providing the semiconductor chips to end users. Activities: delivering the chips to companies that will use them in their products. Sustainability feedback and management. Purpose: gathering feedback and managing the environmental impact of the manufacturing process. Activities: collecting feedback from customers and implementing sustainable practices. Integration. Purpose: integrating the semiconductor chips into electronic devices. Activities: incorporating the chips into various products like smartphones, computers, and other electronics. Etching. Purpose: refining the patterns on the wafer. Activities: using etching techniques to further define the circuit patterns and remove any remaining unwanted materials. Summary. This flowchart video provides a comprehensive overview of the complex and multi-step process involved in semiconductor manufacturing. Each stage is crucial in ensuring the quality and functionality of the final semiconductor devices that power modern electronics. Understanding this process is essential for anyone involved in the semiconductor industry or studying this field. Sample AI/ML result. Defect analysis. Defect analysis focuses on identifying and analyzing defects in semiconductor products. It helps determine the root cause of issues, whether they are due to design, material, or manufacturing problems. The video titled Design Issues Visible is a bar chart comparing different categories of issues against the total production count. Here's a detailed explanation of each component. Key components. Y-axis count represents the number of issues or total production units, ranging from 0 to 1000. Categories. Design issues, represented by a red bar, indicating defects in the design process. Material defects, represented by a blue bar, indicating issues with the raw materials. Manufacturing issues, represented by a green bar, showing problems that occur during the manufacturing process. Total production, represented by a yellow bar, indicating the total number of units produced. Observations. Design issues, approximately 150 defects. Material defects, around 100 defects. Manufacturing issues, about 50 defects. Total production, 1000 units. Interpretation. Proportion of issues. Design issues, red, are the highest among the categories, with about 150 defects. Material defects, blue, follow with around 100 defects. Manufacturing issues, green, are the lowest with about 50 defects. Overall production, the yellow bar representing the total production count, 1000 units, highlights that despite these defects, a significant number of units are produced. Summary. This bar chart is a visual representation of the different types of issues encountered in the production process and their respective counts. It provides a clear comparison between the number of defects in design, material, and manufacturing processes against the total production, which can help in identifying critical areas for improvement to enhance overall production efficiency.